Quantum physics describes the behavior of particles on the smallest scales, such as atoms and subatomic particles. The term quantum comes from the Latin word quantus, meaning how much. Light can behave as both a wave and a particle, a phenomenon known as wave-particle duality. The famous double-slit experiment demonstrated that particles like electrons can act like waves. Quantum entanglement means two particles can become linked, influencing each other instantaneously, regardless of distance. Albert Einstein called quantum entanglement spooky action at a distance. The Heisenberg uncertainty principle states that you cannot precisely measure both the position and momentum of a particle at the same time. Schrödinger's cat is a thought experiment that illustrates quantum superposition, where a particle can be in multiple states simultaneously. Particles can tunnel through barriers in a phenomenon called quantum tunneling, defying classical physics. Quantum physics challenges the idea of a deterministic universe, introducing probabilities instead of certainties. The Planck scale is the smallest scale where quantum gravity effects are expected to become significant. The smallest amount of energy that can be absorbed or emitted is called a quantum. Max Planck, the father of quantum theory, discovered that energy is quantized in discrete packets. Quantum superposition allows particles to exist in multiple states at once until measured. Quantum computers use qubits, which can represent both 0 and 1 simultaneously due to superposition. Photons are the fundamental particles of light and other forms of electromagnetic radiation. Virtual particles can pop in and out of existence in a vacuum, thanks to quantum fluctuations. Quantum mechanics governs the entire universe, but only becomes noticeable at extremely small scales. The speed of light is the maximum speed at which information can travel, even in quantum systems. At the quantum level, particles exhibit wave-like properties, spreading out over space like ripples in a pond. Quantum physics has revolutionized technologies like semiconductors, lasers, and MRI machines. The Planck constant, h, is a fundamental constant that describes the scale of quantum effects. The concept of spin in quantum mechanics does not mean particles physically rotate, but represents intrinsic angular momentum. Quantum foam refers to the idea that space-time at the smallest scales is constantly fluctuating. Quantum teleportation allows the state of a particle to be transferred instantly to another particle. Quantum decoherence explains how quantum systems lose their superposition states when interacting with their environment. Particles in quantum mechanics don't have definite positions until they are observed or measured. The energy levels of electrons in an atom are quantized, meaning they can only occupy specific orbits. Quantum mechanics is essential for understanding the behavior of semiconductors used in electronics. Bose, Einstein condensates, are a state of matter formed at temperatures close to absolute zero. The quantum Zeno effect shows that continuous observation can prevent a particle from changing its state. A qubit can exist in a state called entanglement, where its state depends on another qubit's state. Quantum cryptography uses principles of quantum mechanics to create nearly unbreakable encryption. Quantum states collapse into a single reality upon observation, a phenomenon central to the Copenhagen interpretation. Quantum particles can interfere with themselves, producing wave-like interference patterns. The Casimir effect shows that quantum fluctuations can create measurable forces between objects. Quantum field theory combines quantum mechanics with special relativity to describe particle interactions. Quantum systems can exist in non-local states, meaning particles can influence each other instantly over large distances. The EPR paradox, proposed by Einstein, Podolsky, and Rosen, questioned the completeness of quantum mechanics. The many worlds interpretation suggests that all possible outcomes of a quantum event exist in separate universes. Quantum mechanics underpins our understanding of chemical bonds and molecular structures. The quantum harmonic oscillator describes how particles, like vibranium, vibrate at quantized frequencies. 0. Point energy refers to the lowest energy state of a quantum system, which is never truly at rest. The photoelectric effect, explained by Einstein, showed that light behaves as particles called photons. Quantum entanglement has been experimentally confirmed over distances greater than 1,000 kilometers. Quantum mechanics predicts that particles can be created and destroyed, violating classical conservation laws locally. At the quantum level, time may not flow as a continuous entity, but as discrete intervals. The Born rule in quantum mechanics provides probabilities for measurement outcomes, not certainties. Particles can exist in regions known as quantum wells, where their energy is confined. Quantum annealing is a technique used by quantum computers to solve optimization problems. The Feynman path integral shows that particles take all possible paths simultaneously in quantum mechanics. Quantum mechanics applies to all particles, but its effects are typically only noticeable at very small scales. Black holes emit radiation, known as Hawking radiation, a quantum mechanical phenomenon. Quantum coherence allows particles to maintain their wave-like properties over time. In quantum mechanics, the vacuum is not empty, but filled with energy and virtual particles. Quantum entanglement has been proposed as a method for faster than light communication, though it does not transmit usable information. Quantum tunneling plays a key role in nuclear fusion, powering the sun and other stars. The uncertainty principle makes it impossible to predict a particle's behavior with complete accuracy. Quantum mechanics forms the foundation of modern physics, alongside general relativity. Quantum particles do not have definite trajectories like classical particles. Their paths are probabilistic. Quantum dots are nanoscale particles that have unique electronic properties due to quantum confinement. Observing a quantum system can fundamentally alter its state, known as the observer effect. The collapse of a quantum wave function is a key concept in understanding how measurement affects reality. Quantum levitation, seen in superconductors, occurs due to magnetic flux spinning. Superposition allows quantum computers to perform many calculations simultaneously. Quantum teleportation does not move particles, but transfers their quantum state to another particle. Photonic quantum computing uses light particles to process information. The principle of complementarity states that quantum objects can exhibit wave or particle behavior, but not both at once. Quantum spin liquids are materials with entangled magnetic moments that do not order, even at low temperatures. The Bell inequality experiments confirmed that quantum entanglement is real and cannot be explained by classical physics. Quantum. Random number generators use quantum phenomena to produce truly unpredictable numbers. quantum wave function provides a mathematical description of a particle's probabilities. Quantum noise limits the precision of measurements, even with perfect instruments. Quantum biology explores how quantum mechanics affects biological processes like photosynthesis. Topological quantum computing uses quasiparticles to perform calculations in a fault-tolerant manner. Quantum algorithms, like Schur's algorithm, can factorize large numbers much faster than classical ones. The de Broglie hypothesis suggested that all matter has wave properties. Quantum key distribution ensures secure communication by using the principles of quantum mechanics. Quantum teleportation relies on entanglement and classical communication to transfer information. The Standard Model of particle physics incorporates quantum mechanics to describe fundamental forces. The Pauli exclusion principle states that no two fermions can occupy the same quantum state simultaneously. Quantum walk algorithms mimic the behavior of quantum particles for solving complex problems. Quantum computing could potentially revolutionize fields like cryptography, medicine, and artificial intelligence. The quantum Hall effect demonstrates the quantization of electrical resistance in two-dimensional systems. The principle of superposition enables the creation of quantum supercomputers with massive computational power. In quantum mechanics, particles can interfere destructively canceling out their wave functions. Quantum annealing is being explored as a method for solving optimization and machine learning problems. In quantum mechanics, the observer is part of the system, blurring the line between measurement and reality. Quantum systems can exhibit delayed choice, where decisions may now affect measurements in the past. The fine structure constant, approximately 1/137, plays a fundamental role in quantum physics. Quantum states can be represented geometrically on a Bloch sphere. In quantum computing, quantum key distribution relies on the fact that measuring a quantum system disturbs it. Quantum superfluidity occurs when particles flow without resistance at extremely low temperatures. Quantum lattice models help explain high temperature superconductivity. The concept of quantum foam suggests space-time is not smooth, but turbulent at the Planck scale. Quantum error correction is essential for building reliable quantum computers. The holographic principle suggests that all the information in a volume of space can be described on its boundary. Quantum spin networks are theoretical models used to study the geometry of space-time. Quantum cryptography ensures that any attempt to intercept communication will leave detectable traces. Quantum mechanics implies that empty space is never truly empty, but filled with quantum fluctuations.